Good evening. It is 6 p.m., but participants are yet to join. So we will wait for a few more minutes before we get started. Thank you. Good evening and welcome to the live session for the course on Computational Science and Engineering. This course is taught by Professor Ashok Dey, who is a member of the faculty of the Department of Aerospace Engineering at IIT Kanpur, and I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. In the last session, we had been looking at partial differential equations, and we will continue our discussion. The next topic in the module on partial differential equations uh, considers the Neumann problem. And a Neumann problem in the plane consists of finding a function that is harmonic on a given region D and whose normal derivative assumes given values on the boundaries C of D. And the problem has the standard form nabla square u, where u is a function of x y equals 0 on D, dou u dou n equals gx of y, g of x and y for x, y, and c, with g of x, y, a given function defined on the boundary of C. And while the problem deals with finding a solution or finding a function, first we must also know as to what are the conditions that guarantee the existence of such a solution, if any. And that condition is given here. And the condition is the cyclic integral on the boundary C of dou u dou n ds is equal to the cyclic integral of the boundary C of the function g times ds, and both of these must equal 0. This means that vanishing of the integral of the given normal derivative over the boundary of the region is a necessary condition for the Neumann problem to have a solution. If the integral of g over c is not 0, then the given Neumann problem has no solution. And it can also be extended to the case when the region D given to us is not really a bounded region and C is not necessarily a closed curve. For instance, when we are only working with the right quarter plane given by x and y both greater than or equal to 0, here the region is unbounded and its boundary curve consists of the non-negative x and y axes. And let us understand this concept further by solving an illustrative example. We are asked to check whether the given Neumann problem has a solution, and the problem given to us is nabla square u equals 0 for x lying between 0 and 1 and y lying between 0 and 1. And dou u dou n is equal to 0 on the left top and lower sides and equal to y square on the right side of the square. So let me just sketch the domain for easier understanding. So dou u dou n is equal to 0 on the left top and lower sides. And on the right side, dou u dou n is equal to y square. So let us just rewrite the necessary condition for existence of solution for a Neumann problem. it was the cyclic integral of G times ds is 0. G, by the way, is equal to do you do it. Now, the curve that we are given here is a closed curve, but we can also divide it into four curves for ease of computation, as we can see, because these are the sides of a square. So along any given one side, say for this lower side here, we are seeing that y is constant while only x is varying. Whereas on the right or left sides, x is constant while y is varying. And so by breaking up this domain into four curves, we can make the computation easier. So let us just demarcate these curves as say C1, C2, C3, and C4. So what we're trying to do is break this cyclic integral uh, between the curves. And let us now perform this integration one by one over each of the sides. So first, over the side C1, over this side, we are told that dou u dou n or g is equal to 0. Therefore, the integral over C1 of g ds is also 0. And I mean, with this, you would see how breaking up the domain into the following curves made it easier. Now, let us do it over the curve C2. Here, dou u dou n is given to us as y square. We have to integrate g times ds. But what is this ds? ds is just a very small element or a position vector along this given direction. So generally, ds is equal can have the two components dx along the I hat direction and dy along j hat direction. But along C2, that is along this right side here, there is variation only in the y direction because x is constant. And so ds is simply equal to dy along j hat direction, and the norm of this vector will simply be equal to the dy because j hat is just a unit vector. So when we are trying to integrate y square over C2 with ds, this is simply dy. This will give us y cubed by 3, and y in this case is varying between 0 and 1, as you can see from the figure. So this gives us 1/3. Integrating over C3 will again give us 0, because if I remember, yes, along these sides also, g is simply 0. And same is the case over C4. Now, The necessary condition was for the integral GDS over the whole curve equal to 0. But here we are seeing that for the entire cyclic curve, the integral of GDS, which is equal to the sum of integrals along each of the four curves C1, C2, C3 and C4 is 1/3, which is not equal to 0. And so the given problem does not have a solution. Now, with that clear, let us move on to the next question. We are asked to solve the heat equation, which is the relation for which is also given to us, which is simply ut equals alpha square uxx, or dou u dou t is equal to alpha square dou tu dou x2. So this is the heat conduction equation in one dimension only along the x direction. And this is to be solved on a rod of length 10 units. The initial temperature distribution is also given to us, where the rod had initial temperature distribution given by the function u at x0 is equal to 10x. The boundary conditions are u at 0 comma t is equal to 80 and u at 10 comma t equals 20. So on the left and the right boundaries. Further, besides solving the heat equation, we are also asked to sketch approximate trends of the solution at a few time instances to show the evolution of the temperature. So let us start solving. The heat equation has already been discussed by Professor Day during his lectures, so I will not delve much into the derivation and the principles. We'll directly start solving it. So as given to us, dou u dou t is equal to alpha square dou to u dou x2 with the condition, initial conditions, u at 0 comma t is equal to 80, sorry, with the boundary condition u at 0 comma t is equal to 80 and u at 10 comma t is equal to 20 for all times greater than 0, and for t equal to 0, that is the initial condition, u at x comma 0 is equal to 10x over the entire length. So 0 less than equal to x less than equal to 10. And typically, as Professor Day has already described in the sessions, the heat equation is amenable to solution by something called the separation of variables. So let us do that. And here what we are doing is, we have a function u in this case, which is a function of both space and time, so x and t, and we are assuming that this function u is actually a product of two functions, one which is entirely a function of space or location, that is x variable, and the other function which is entirely a function of the t variable. And with this assumption, let us see what happens. Typically, the way we go about is we plug in the boundary conditions. Say u at 0 comma t is equal to 80 would imply that x at 0 and t at all times t is 80, which implies that the value of the function t at all time steps is given by 80 by x at 0. Now, this is worrisome because this is simply a constant. And previously, whenever we have dealt with solutions that could be achieved by a separation of variables, the RHS would often be zero. And so we would end up with a scenario with something like x at 0 times t of t is 0. Since t of t cannot be 0 at all time steps, so x of 0 must be equal to 0, and we continue. But here we see that the RHS is non-homogeneous. That is, it has a non-zero value. So is there still a way to solve this? The good news is that there is. And what we'll do is we will modify our solution strategy a little to account for this non-homogeneous RHS and try to still use this method of separation of variables for solving this partial differential equation. So to account for this non-homogeneous part, let us redefine our function u as the sum of two functions, one capital U, which is a function of both x and t, and another function psi, which is a function only of x. And we will see how this helps. So with this substitution, dou u dou t then simply becomes dou capital U dou t, and dou 2u dou x2 becomes dou 2 capital U dou x2, but psi is also a function of x, so psi double prime of x. Now we compare this with the standard form of the heat equation. So here what is given to us is simply dou capital U dou t is equal to alpha square dou 2u dou x2. So dou 2 capital U dou x2 plus psi double prime of x. And let us see how this compares with the usual form, which is simply dou u dou t equals alpha square dou 2u dou x2. So this psi double prime x term appears to be extra. And take care of that. Let us work with the assumption that psi double prime of x is 0, which would imply that psi prime of x is a constant. Let us say that is d1, which would imply that the function psi has the form d1x plus d2, where d1 and d2 are both constants. Now let us apply the boundary condition again, which was u at 0 comma t is 80, which implies that capital U at 0 comma t is psi at 0 with 80. Now again, if we recollect the way we were solving some typical PDEs, such as, for instance, with the RHS 0, so we are already familiar. It's a homogeneous RHS, that is U at 0 comma t is 0. But in the present case, we have an RHS of 80. So again, a second assumption, if we assume that u of 0 comma t is 0, this would mean that this RHS, non-homogeneous RHS AT is taken care of by the size of at 0 term. Psi at 0 must be AT, and this can help us find the value of D1 and D2. So psi at x is equal to D1x plus D2, which implies that psi at 0 should be equal to D1 times 0 plus D2, which is 80, or D2 would equal 80. Let us apply the other boundary condition, which was u at 10 comma t is 20, which implies that u at 10 comma t plus psi at 10 is 20. Now remember, for psi we have found d2, but we still need to find the constant d1. So if we can use the given second boundary condition to derive a second relation for psi, we may be able to find d1. So to facilitate this, if we assume u at 10 comma t is also 0, then psi at 10 will equal 20, but psi is of the form d1x plus 80. So psi at 10 is equal to 10 d1 plus 80, which we are told is equal to 20. This would give us 10 d1 is equal to minus 60, or d1 is equal to minus 6. And so we have the form of psi of x, which is equal to minus 6x plus 80. Now that we have psi of x, let us now apply the initial condition. So initial condition given to us is u at x comma 0 is equal to 10x. And since u at x comma 0 is equal to capital U at x comma 0 plus psi is a function entirely of x, so psi of x is equal to 10x, which implies that capital U at x comma 0 and psi is given to us by minus 6x plus 80 is equal to 10x, which implies that capital U at x comma 0 is equal to 16x minus 80. And this might look familiar. This can be taken as the initial condition for U, that is capital U at x comma 0 is given as 16x minus 80. Let's see if we have some other conditions. We have a boundary condition here, U at 0 comma t, which by the way we assume, and based on our assumption we are devising this framework. And the second boundary condition, again, U at 10 comma t is 0. So now that we have these three conditions, we can in fact reframe the given question in terms of the variable capital U. we have dou u dou t equals alpha square dou to u dou x2, where we have the boundary condition u at 0 comma t is equal to 0 and u at 10 comma t is also equal to 0 for all t greater than 0, and the initial condition u at x comma 0 is equal to 16x minus 18. Now, the RHS now both the boundary conditions are homogeneous because their RHS are 0, and we are already familiar with solving problems of this type. So let us jump into it immediately and use the separation of variables method again. So let the function capital U, which is a function of both x and t, be equal to the product of two functions, one entirely of x and the second entirely of t. In this case, dou u dou t would equal x t prime and dou to u dou x2 would equal x double prime t. If we substitute this back into the original heat equation, that is the one we framed in terms of capital U, dou u dou t becomes alpha square dou to u dou x2, which would imply that xt prime equals alpha square x double prime t, which would imply that x double prime by x equals minus t prime by alpha square t, which is equal to minus lambda, where minus lambda is the separation constant. We had also discussed why there is a negative sign here, and that is because of convention, because it makes further calculations somewhat simpler. Now, if we apply the boundary conditions that we framed, then u at 0 comma t is 0 implies that x at 0 times t at t is 0, and since t at all times t cannot be equal to 0 for a non-trivial solution, x at 0 must be equal to 0. Similarly, for the other condition, u at 10 comma t equals 0 implies x at 10 times t at t is 0. And since the value of the variable capital T at all times cannot be equal to 0 for a non-trivial solution, therefore x at 10 must equal 0. Now let us solve the equation concerning x and its derivatives. So x double prime by x equals minus lambda, which implies that x double prime plus lambda x equal to 0 with the conditions x at 0 is 0 and x at 10 is also 0. And this is the form of the Sturm-Liouville problem, which we had discussed in the previous session. We will not go into deriving the entire solution again. We already know how it works. We take cases on lambda. Uh, we assume that it is less than, greater than, or equal to 0. And with this assumption, we try to find non-trivial solutions. And for this equation of this form, x double prime plus lambda x equal to 0 with the conditions x at 0 is 0 and x at 10 is 0, we know that the eigenvalues are lambda n equals n square pi square by 10 square, which is equal to n square pi square by 100. And the eigenfunctions our xn equals sin n pi by lx. Here L is equal to 10, so sin n pi by 10x. Let's now solve the equation for t, which was yeah, I put a extra negative sign here. The equation for t was t prime by alpha square t equals minus lambda. T prime by alpha square t equals minus lambda, which implies that t prime plus lambda times alpha square t equals 0. But we already have the values of lambda, which implies that t prime plus lambda is equal to n square pi square by 100, n square pi square by 100 times alpha square t is equal to 0. This would imply that Tn is equal to e power minus n square pi square by 100 alpha square time. Now we have both the eigenfunctions for x and t. So the fundamental solution of the function Qn, which is the product of x and Tn, is equal to e power minus n square pi square by 100 alpha square t times sin n pi by 10x. And the solution for the problem is actually the series sum of all such possible functions. So we have n going from 1 to infinity, some coefficient cn times un, so e power minus n square pi square by 100 alpha square t sin n pi by 10x. And we must find this coefficient cn. And here we can make use of the initial condition which we have not used yet. U at x comma 0 is equal to 16x minus 80. So from the initial condition, U at x comma 0 is equal to 16x minus 80. And if you also put U at x comma 0 in this series sum given here, facility summation n equals 1 to infinity Cn. The second term, which has t in its exponent, simply goes to 1 because e power 0 is 1 and sin n pi by 10x. Again, if you look at this carefully, this is simply the Fourier sine series expansion of the function given to us. So this is simply the Fourier sine series expansion of the function 16x minus 18. And so, since this is a Fourier sine series expansion, we already know the way to find this coefficient Cn. This will be equal to 2 by L, or in this case 2 by 10, integral 0 to L. So 0 to 10 fx sine n pi by L, here L is equal to 10, x dx. And just to simplify this a bit further, this equals 1 by 5 integral 0 to 10. We can actually break it up into two integrals. 16x sine n pi by 10x dx, and the second term minus 80 integral 0 to 10 sine n pi by 10 x dx. And this consists of integration by parts for the first term, and for the second term is just a single integral. So typically represented by integral of u by dx, where u and v are both functions of x. And depending on your choice of u and v, the simplification can be, or the subsequent steps can be simple or complex. And so we have to make a clever choice. Here, let us take u equals, okay, x, and v equals sine n pi by 10x. And you're also free to choose the other way and see if it makes life any easier. With that choice, let us see what this computes to. Cm becomes 1 by 5. We have the 16 coming out. U into integral v dx and this is to be evaluated between 0 and 10 minus just to be clear, 16 is multiplying all of it, minus integral of differential of u, which is simply 1, into integral of v dx, so cos n pi whole dx. And for this third term, we have minus 80 times cos n pi by 10x by minus n pi by 10. We are at between 0 and 10. Let us simplify this. So Cn then equals 1/5 into 16 times. What is this first term? For x equals to 10, this becomes 10 cos n pi, which is minus 1 power n, by minus n pi by 10, minus this evaluated at 0, which is simply 0, and then we have this second term, which is simply the integral of cos n pi by 10 x dx, which will become so minus minus plus sin n pi by 10 x by n pi by 10 square evaluated between 0 and 10 plus the third term, which is 80 cos n pi is minus 1 power n and cos 0 is 1 by n pi by 10. Now for the second term here, we see that sin n pi is also 0 and sin 0 is also 0. So we only have the first and third term surviving. This is 1600 minus 1 power n plus 1 by n pi. The second term is 0. So the third term in this case is simply 0. And we have 800 times minus 1 power n minus 1 by n pi. And let's see if we can simplify this further. So this becomes 320 minus 1 power n plus 1 again becomes plus 160 minus 1 power n minus 160. In fact, we can also remove minus 1, put it ahead of this. So this becomes minus 160 by n pi times minus 1 power n minus 1 sorry plus 1 yeah, this is it. And now we have the coefficient, so this is actually equal to Cn. So therefore the solution becomes u at x comma t was the series solution n equals 0 to infinity, sorry, n equals 1 to infinity because we have a sine series here. This coefficient is 160 by n pi minus 1 power n plus 1 times x and tn e power minus n square pi square by 100 alpha t times sine n pi by 10x we can see one additional thing, and that is because of the presence of this minus term minus 1 power n. So when n is odd, minus 1 power n plus 1 equals 2, whereas n is even, minus 1 power n plus 1 equals 2. And so we can even further simplify the solution by only the even terms in this series expansion. So the final solution is u of x comma t equal to the sum of only given n, and if I supply 2 here, this becomes minus 320 by n pi e power minus n square pi 100 times alpha square t to sine n pi by 10 x. So this is the solution of the heat equation, and we're also asked to sketch the approximate trends of the solution at few time instances. So let us do that. So okay. So these two vertical lines correspond to x equals 10 and x equals uh, and the vertical will correspond to u of x comma t. And let's have a few temperature levels for ease of sketching. So say what are the relevant numbers here? AET we have 20, 10x, 10x. So the maximum is 10 into 10, 100. So maybe 20, 80, and 100. This is u equals 20, u equals 80, and u equals 100. In the question, we were told that the initial condition u at x comma 0 is equal to 10x. This is just a straight line with a zero intercept. And given the boundary conditions, u at 0 comma t is 80 and u at 10 comma t is 20. This means that we are holding the left hand at 80 and the right hand at 20 units. And so eventually, after a very long time has passed, or the solution has reached, the system has reached a steady state. The temperature of the system at the left hand should also be 80, and the temperature at the right hand should also be 20. We can also sketch that. And since there is no transience, the there's a balance of flux coming in and going out. And so the slope of this curve in the left and right hand sides will also be constant. And for a curve with constant slope, it will only be a straight line. So this is that. The blue curve corresponds to equal to 0, and the red curve corresponds to tending to infinity after a very long time. So let us have a few states in between, and how will the temperature evolve? Now the left hand side is held at 80 degrees, and so a point which is very close to this left boundary will also be at 80 degrees. However, initially the system had a temperature distribution following the blue line here. And so what the system will do is, starting at 80 near the left hand, it will try to remain as close to the original distribution as possible, but it is forced to go to 20 at the right hand side. After a slightly longer time period, a slight increase in time, and say after an even longer gap of time, it will now resemble the final distribution more and more. So this is E3, and we have even less than T2, less than T3. So this is how the computer distribution is given the initial and boundary conditions. Next, we'll continue discussing about partial differential equations after a short break. Let us reconvene in some time. Let us now continue with our discussion of partial differential equations. And as Professor Day has already described in his lecture, uh, PDEs are classified into multiple types, and some of them are elliptic, hyperbolic, and others. So let us look at them one by one. And the elliptic partial differential equation we consider is the well-known Poisson equation, that is nabla square u, which is equivalent to del 2 u del x2 plus del 2 u del y2 is equal to some function f of xy uh, on the region R, where x lies between a and b and y lies between c and d, and as denotes the boundary of R. And if a and g are continuous on their domains, then there is a unique solution to this equation. And while we have been discussing about the analytical solution of these equations, we should also spend some time talking about the numerical solution of these equations, because when solving them in any computer-aided engineering software, what we're actually doing is solving them numerically. Numerical solutions, which are also so focused on this course, have the additional advantage that even for problems or say differential equations which do not have a closed, strictly a closed form solution, they may still progress or maybe amenable to solution by numerical techniques. And these solutions will be approximate, but for an engineering application or from an engineering standpoint, they will be good enough. So let us see how such equations are solved numerically. And the first step in a such solution is the discretization of the domain into discrete points known as grid points or mesh points. So the first step is to choose integers n and m to define the step sizes that we're taking in either direction. The step size along the x direction is given by h, which is equal to b minus a by m. That is, we are dividing the domain between b and a into n parts. And along the y direction, the step size is k, which is equal to d minus c by m. That is, along the y direction between c and d, we are dividing the domain into m parts. And these they are equal parts, as shown here. And then we end up with these mesh points or grid points, at which we actually solve the equation. And for all other points in the continuum, we simply extrapolate the solution from these grid points based on some approximative algorithm. The lines x equals xi and y equals yi, that is the horizontal and vertical lines shown here, are called grid lines, and their intersections are the mesh points of the grid. Now, for each such mesh point in the interior of the grid, because at the boundary we are only applying the boundary conditions, and also at the boundaries we may not have enough information to actually derive a generalized formulation. So whenever we're talking about these formulations, they're actually well within the domain and away from the boundaries. So for a mesh point in the interior of the grid xi yj, for I equals 1 to 2n minus 1 and j equals 1 to m minus 1, we can use the Taylor series expansion in the variables x about xi to generate the centered difference formula, which will take the form as shown in equation 12.2. Again, we can repeat this procedure for the variable y about yj to generate the centered difference formula in y. And this is given in equation 3. And using these formulas, we can express the Poisson equation at any point xi yj in the form u at xi plus 1 comma yj minus 2u at xi yj plus u at xi minus 1 yj by square plus u at xi plus 1 minus 2u xi yj plus u at xi yj minus k square is equal to f of xi yj plus h square equal del 4u plus 4 zeta I yj plus k square by 12 del 4u del y4 xi eta j. And boundary conditions are also expressed as we can see at x0, y0, xn, and ym. Now, in difference equation form, in something called the finite difference method, which you might already have heard of and encountered even whenever solving a problem numerically. And this has the form given in equation 12 by 4. 2 times s square by k square plus 1 into wij minus wi plus 1 comma j plus wi minus 1 comma j minus h by k whole square times wi j plus 1 plus wi j minus 1 equals minus h square f of xi ij. So you see, we are relating the information at any domain point xi yj to other domain points such as at ij itself, at I plus 1 nj, I minus 1 nj, I j plus 1, and I j minus 1. And the typical equation in 12.4 as given here involves approximation to the information or the variable u at xy at the points xi minus 1 yj, xi yj, x I plus 1 yj, xi yj minus 1, and xi yj plus 1. It can also be visualized here, where we are trying to find the information about the point given by the blue cross in the center. And to find this information, we are making use of the information available about these neighboring points to the north, east, south, and west of our point of interest. Now, whether the information at all those points is available or not is a separate story. And in the scenario where, say, information about at any or all of those points is not available, how we go about solving for the region in the center, then uh, these are discussions for a separate day. But this is basically how we are trying to attempting to solve for information at the center point. And formulating our problem in this way produces an n cross n minus 1 m minus 1 cross n minus 1 m minus 1 linear system. What we're solving for is an approximation wij to the exact solution u at xi yj at the interior mesh points. And as we can see in the illustration to the right, we can relabel our system. And here the mesh points are simply consecutively labeled from left to right and top to bottom. Labeling the points in this manner ensures that the system needed to determine wij is a banded matrix with bandwidth at most 2n minus 1. So with these equations that we just saw, let us just try to formulate a solution for a given problem. We will not really try to solve the entire question and arrive at a numerical solution per se. But what we will try to do is, given the equations in the previous section, we'll try to maybe arrive at the matrix form of the solution, and then which can always be solved by using some computer program. So let us try to do this. We are asked to determine the steady state heat distribution in a thin square metal plate with dimensions 0.5 meter by 0.5 meter using n equals m equals 4. In this case, two adjacent boundaries are held at 0 degree, and the heat on the other boundaries increases linearly from 0 degrees Celsius at one corner to 100 degrees Celsius where the sides are meeting. So again, it might be wise to sketch this problem for easier visualization. And say this is our domain. Now we have to divide it, and we are told that along the x direction, we have to divide it into four sections. So similarly along the y into four. Each of these sides is 0.5 meters, so this is 0.5 and this is 0.5 as well. We are given the choice that two adjacent boundaries are held at 0 degrees Celsius. So just let us take the left and bottom boundaries at those two temperatures, but any two adjacent boundaries will do. So this is u at 0 comma y is set to 0 and bottom one is u at x comma 0. This is also set to 0. Now for the other two sides we are told that the heat increases linearly from 0 degrees C at one corner to 100 degrees C at the corner where the sides are meeting. So at this corner temperature is 100 degrees C, whereas at the bottom is 0. Also for this corner it is 0 and the temperature is changing linearly. So with all of this information we can very quickly say that given that this length is only 0.5 meters, u at 0.5 comma y should be equal to 200y, because at the bottom corner y is 0 and so u is also 0. At the top y is 0.5, so u is 100. And for the top face again, u at x comma 0.5 should be equal to 200x. Again, because of similar reasons. And now we must make use of the equation given to us. I'm just reproducing it here. Equation 12.4 will eventually take the form for wij minus wi plus 1j minus wi minus 1j minus wij minus 1 minus wij plus 1 is 0, where I is equal to 1, 2 and 3, and j is also equal to 1, 2 and 3. And now let us, just for convenience sake, let us assume the nomenclature which was discussed in the slides. So the grid point here is P1, P2, P3, P4, P5, P6, P7, P8, P9. And as we discussed, we are solving for points on the interior, not really on the boundaries. Now, we can frame the equations separately for each of these points. And I am writing that here. So for P1, The equation becomes 4W1 minus W2 minus W4 equals W at 0, comma 3, so at one of the boundary, plus W at 1, comma 4. And I will request you to kindly verify whether these equations are written correctly or not, because I might make mistakes. For P2 again, following the similar skeleton just by changing the indices, 4W2 minus W3 minus W1 minus W5 equals W2, comma 4. For P3, this becomes 4W3 minus W2 minus W6 equals W at 4, comma 3 plus W at 3, comma 4. For P4, this becomes 4W4. Again, you notice that the template for all of these equations is the same. It's just the value of the indices which is changing. Minus W5 minus W1 minus W7 is W at 0, comma 2. So again, using one of the boundary conditions. For the point P5, 4W5 minus W6 minus W4 minus W2 minus W8 is equal to 0, because we are making use of the corner point. For point P6, 4W6 minus W5 minus W3 minus W9 equal to W4, comma 2. For the point 7, 4W7 minus W8 minus W4 because W at 0, comma 1 is W at 1, comma 0. For point P8, 4 times W8 minus W9 minus W7 minus W5 equals W2, comma 0. Again, in making use of the boundary conditions. And finally for the point P9, 4W9 minus W8 minus W6 equals W30 plus W41. Let us also take a moment to write all the boundary conditions as per our choice. So we have chosen the left and the bottom edges to be held at 0. So the boundary conditions will become W1, comma 0 equals W2, comma 0 W3, comma 0 plus W0, comma 1 W0, comma 2 equals W0, comma 3, and all of these are held at 0. And if we look at the other points which are lying on the right and top edges, we have W1, comma 4 will equal W4, comma 1. So this point and this point, and here, because of the linear variation of temperature, the temperature would simply be 25. Then at 2, comma 4 and W4, comma 2, where again because of linear variation this will be 50. W3, comma 4 and W4, comma 3, it is equal to 75. And W4, comma 4, we know that it is 100. Now, we see that all of these equations involved variables from W1 to W9. So if we write it in matrix form, and it will be a pretty large matrix, so let us be careful. Sorry about that. 4 minus 1 0 minus 1 0 0 0 0 0 minus 1 4 minus 1 0 minus 1 0 0 0 0 0 minus 1 4 0 0 minus 1 triple 0 minus 1, 0, 0, 4 minus 1, 0 minus 1, 0, 0, 0 minus 1, 0 minus 1, 4 minus 1, 0 minus 1, 0, 0, 0 minus 1, 0, minus 1, 4, 0, 0 minus 1, triple 0, minus 1, 0, 0, 4 minus 1, 0. So as you can see, the matrix is consisting entirely of minus 1, 4, and 0. 0, 0, 0, 0, minus 1, 0, minus 1, 4, minus 1, 0, 0, 0, 0, 0, minus 1, 0, minus 1, 4. This is our coefficient matrix. Times W1, W2, W3, W4, W5, W6, W7, W8, W9 equals the RHS 25, 50, 150, 0, 0, 50, 0, 0, 25. And if we solve this matrix, we will end up with the temperature at each of those interior points marked from P1 to P9. We will also look at the pseudocode for this if the time permits, because it is a fairly large pseudocode. For now, let us look at the next type of partial differential equations. We discussed about elliptical PDEs. Now let us talk about parabolic PDE. And even without realizing, we have already encountered the parabolic PDE before in the form of the diffusion equation, or in one of its more commonly encountered forms called the heat equation, which was of the standard form dou u dou t equals alpha square dou to u dou x2 for 0 less than x less than L and t greater than 0. Subject to the boundary condition u at 0 comma t equals u at L comma t is 0 for all time greater than 0, and subject to the initial condition u at x comma 0 is equal to fx for 0 less than equal to x less than equal to L. Again, for the forward difference scheme, we obtain the difference method using Taylor series in T to form the difference quotient as given in equation 12.7. Again, for the from Taylor series in X to form the difference quotient as given in 12.8. And then for the parabolic PD at all interior grid points, we can have the solution by from solving the equation using these two difference coefficients. W at ij plus 1 minus wij by k minus alpha square wi plus 1j minus 2wij plus wi minus 1j by h square equals 0, where wij approximates the exact field variable u at xi comma tj. And solving equation 12.9 will give us this form. And we also have the initial conditions. W at 0 comma 0 is f of x comma 0, w at 1 comma 0 is f of x1, and so on. So these are all the initial conditions at t equal to 0. Now for the next time step, that is by incrementing the time variable by this time step, for example k, we can obtain the value of these variables at time step 1, W01, W11, W21, and so on. And the explicit nature of the difference method implies that the m minus 1 into m minus 1 matrix can be written in this tridiagonal form. What does the explicit nature mean? Explicit nature would imply that the quantity we are solving for is available as an algebraic equation with other known quantities, whereas an implicit formulation would imply that the quantity that we're solving for cannot be expressed as an in an algebraic equation involving only the known quantity. In fact, the algebraic equation or the equation may be such that it involves the unknown quantity both on the left hand and the right hand side, and so that it cannot be simplified further to express the unknown quantity in terms of only known quantities. Then we have the approximate solution. And yes, it's important to be able to visualize the forward difference method, and it is shown here. So when we are trying to solve for information available at the grid point given by this blue cross, we are making use of information available at these three neighboring points, one directly below it, one to the left of the previous point, and one to the right of it. All of these are at a previous time step at tj, and now we are solving at tj plus 1. Since we already solved for tj, the information at all these 3 points is already known to us, and that is why this is an explicit formulation. So say at t equal to 0, which corresponds to this axis here, the information at all of these points was known. And so we solved for the next time step, all of these different grid points using, say if you're solving here, I made use of the information available at these three tick points, and we continued solving. So now that we are at the tj plus 1th step, we already have information about all grid points at the tjth step. And so we can solve for tj minus 1 simply from an algebraic equation. However, despite its apparent ease, the forward difference method or explicit scheme in general are only conditionally stable. That is, they will be stable or the solution will converge only under uh, specific conditions and not generally. And here, convergence is guaranteed. The rate of convergence of the order of k plus h square only if the product alpha square times k by h square is less than or equal to half. And also the required continuity conditions on the solution set are met. However, this would clearly interest us uh, to obtain a method that is unconditionally stable so that we are free in choosing even larger time steps. You see, in this previous case, this time step k had to be sufficiently small so that this entire product is less than or equal to half. But that implies a longer simulation run and perhaps a greater use of computational resources. What if we could use larger time steps and solve for the given problem in a shorter time? And this has led to the search for unconditionally stable methods such as that of backward difference. And this results in equation 12.2 where for information at the point wij, at point ij, it is available in the form wij minus wij minus 1 by k minus alpha square wi plus 1j minus 2 wij plus wi minus 1j by h square is equal to 0. So we see that this cannot really be simplified any further to obtain for wij in terms of all other known quantities. Yeah, the visualization is here as well. So say at the j minus 1th time step, we solve for this point here, and currently we are investigating for this blue cross. Now, since we're solving from left to right, the information at this left neighbor might still be available, but what about this right neighbor? We are yet to solve for it, aren't we? So the information from all other quantities is not known a priori that we can simply manipulate or put in some algebraic relation to obtain the solution for the given point. And this is the implicit formulation. Based on some algebraic manipulation, the backward difference method can take the form 1 plus 2 lambda times wij minus lambda wi plus 1j minus lambda wi minus 1j equals wij minus 1. And the matrix representation for the same is also given in equation 12.13. A few things to note about the coefficient matrix here. The matrix A is positive definite and strictly diagonally dominant, and also tridiagonal, which means that we can use some known algorithms such as TDN or other tridiagonal algorithms to solve for this linear system. And now we'll try to write a pseudocode to solve for the heat equation using backward difference. I will readily supply this pseudocode, and I have borrowed this from reputable sources. But I would request you to implement it and check whether it works for your case. So the objective for this code, of course, is to solve for the heat equation using backward difference. The inputs it will require are the endpoint L, the maximum simulation time, the diffusivity or square root of diffusivity alpha based on how you are formulating the problem, and the time step m greater than equal to 3 and n greater than equal to 1. What this will output is, as I saw, approximations wij to the exact solution u at xi at the time step tj for each grid point I equals 1, 2 to m minus 1 for all time steps j equals 1, 2 to in the first step we set these time and space steps. So set h equals L by m, k equals T by n, and the quantity lambda that we discussed, this quantity right here, as alpha square k by h square. In the second step, we start our iteration. So for I equals 1, 2 to m minus 1, set wi equals f of ih. Step 3, and now we basically start solving for the tridiagonal system. So I'll just put comments. Steps 3 to solve a tridiagonal linear system. And this is how we do it. This is the quantity L1 equals 1 plus 2 lambda, U1 equals minus lambda by L1, and the fourth step, for I equals 2, 3 to m minus 2, we set again Li equals 1 plus 2 lambda plus lambda u at I minus 1 and ui is equal to minus lambda by Li. So 5, we set L at m minus 1 equals 1 plus 2 lambda plus lambda MCU at m minus 2. Step 6, for j equals 1 to capital N, 2 steps 7 to 11. Step 7, set t equals j times k, that is, we are at the current time step, just like previously, I times h meant the current grid point. And z1 equals w1 by l1. Step 8, for I equals to 3 till m minus 1, we set zi equals wi plus lambda z I minus 1 by li. Step 9, set wm minus 1 equals z m minus 1. Step 10, for I equals m minus 2, m minus 3 till 1, set wi equals zi minus ui wi wi plus 1. Step 11, we output t, which is basically the current time step, and for I equals 1 to m minus 1, we set x equals ih, that is the current grid point, and output x comma wi. And iteratively this will solve for the PT equation. The 12th step is to simply stop. We spoke about forward difference and backward difference methods. Let us also discuss perhaps a more efficient way to solve this, which borrows from both of these methods. So a more rewarding method is derived by averaging the forward difference method at the jth step in t, wij plus 1 minus wij by k minus alpha square wi plus 1j minus 2wij plus wi minus 1j by h square equals 0, which by the way will have this local truncation error of the order of h square. And we are averaging the forward difference method with the backward difference method at the j plus 1 at step in t, which takes the form wij plus 1 minus wij by k minus alpha square wi plus 1 j plus 1 minus 2 wi j plus 1 plus wi minus 1 j plus 1 by h square equals 0, which again has the local truncation error of the order of h square. And under the assumption that del 2 u del t2 at xi mu j is approximately equal to the quantity on the right. Then this averaged difference method has local transition error of the order k square plus s square under the assumption that the usual differentiability conditions are satisfied. And this method then becomes known as the Crank-Nicolson method, wherein the quantity lambda is equal to alpha square k square, and it is visualized here. If we are solving for a grid point depicted by the blue cross, we have to make use of available information at all of these other points. So three neighboring points from the previous time step and the immediate left and right grid point from the same time. Then the matrices A and B are given here for ready reference. Let us also quickly look at hyperbolic PDEs. I hope we have the time for it. We looked at elliptic and parabolic PDEs. The third kind is hyperbolic PDEs, which we typically encounter when we're trying to find numerical solutions for the wave equation. The wave equation has the general form del T u del T2 minus alpha square del T u del x2 equals 0, where x varies between 0 and I and t is greater than 0. This is subject to the condition that u at 0 comma 0 equals u at t is 0 for all time t equals 0. That is, the displacement at two ends of the string are 0, and u at x comma 0 some first method that is the string has some initial along with the condition of the slope dou u dou t on the velocity dou u dou t x at x comma 0 was gx. So the string had some initial shape and some initial velocity. The constant alpha in this case will depend on the physical conditions of the problem. And how we go about solving it is that we select an integer m greater than 0 who define the x-axis grid points using h equals L by m. Again, we have to select a time step size k which is just simply greater than 0. Then the mesh points will be defined by along the x-axis as just I times h, along the time axis by j times k. And at any interior mesh point, the wave equation will then take the form of equation 1217, which is dou to u del t2, dou to u dou t2 at xitj minus alpha square dou to u dou x2 at xitj is 0. The difference method here is obtained using the centered reference coefficient for the second partial derivative, and the forms are readily given here. And after further simplification and some assumptions, the advanced time step approximation will become wij plus 1 equals 2 into 1 minus lambda square into wij plus lambda square wi plus 1j plus wi minus 1j minus wij minus 1 as given in equation 1219. The matrix form of the same is also given to us in equation 1222, where we can see that for solving at the time step j plus 1, as we can see from the matrix on the left, we are making use of the information from the jth time step as well as from the j minus 1th time step. So we must have information of two prior time steps. The initial condition will give us information at t equal to 0, but is it really physically reasonable to have information about the time step minus 1? No, and in fact that is obtained from that initial velocity condition that we had. So equations 12, 18, and 190 imply that the j plus 1 time step requires values from the jth and j minus 1th time step. Now the values for j equal to 0 are given as initial conditions, but values for j equal to 1 which are needed to compute at j equal to 2 must be obtained from the initial velocity condition as we just discussed. Again, after further simplification, things take the form of equation 1224 Wi1 equals Wi0 plus k gxi, or each I equals to 1 to m minus 1. Uh, Excuse me, please. This approximation, however, will have the error of order of k instead of order of k square. For some reason, this has come to the subscript. And we can also visualize it here, where when solving for information at the blue cross, which are the t j plus 1th time step, we must make use of information available at three mesh points from the previous time step and one mesh point from the time step before, as illustrated here. So with this discussion, we will conclude this session. Thanks for tuning in to the live sessions for the course on computational science and engineering. I am Sourav Goswami from IIT Bombay, and I look forward to seeing you again in the next session. Thank you.